Hi, I'm Professor Melko, Chemistry PhD, and today we're going to talk about combining Boyle's, Charles, and Lusak's law into a combined gas law, and then talk about ideal gases and the ideal gas equation PV equals nRT. Let's just jump straight into the lecture today. So here's the gas law summaries that we talked about in previous lectures. So you might remember from a previous video where we talked about Charles, Lusak, and Boyle. And had these different equations, P1V1 equals P2V2 for Boyle, V1 over T1 equals V2 over T2 for Charles, and P1 over T1 equals P2 over T2 for Lusak. Okay, it turns out we can combine all these together to make a combined gas law, P1V1, that looks like Boyle's, over T1, like Charles, equals P2V2 over T2. Okay, and this is usually going to be the case when you change the volume of the gas, the temperature and pressure will likely change. So oftentimes we need to use these combined gas laws. So to solve these types of problems, there's 6 different things we need to know. 1, 2, 3, the initial states of pressure, volume, and temperature, and the final states, 4, 5, 6, of pressure, volume, and temperature. So oftentimes the equation, or the problem I should say, will provide 5 of these 6, and you have to solve for the 6th. Just plug them all in like we've done in previous videos on Boyle's and Charles. And feel free to go back and watch those previous videos if you need to brush up on it. So let's look at an example here of a combined gas law. For the initial and final conditions below, solve for the unknown pressure. Right? So here we have one unknown, P2, that we're going to try to solve for given these 5 other data points. So let's remember P1 V1 over T1 equals P2 V2 over T2. And you recall something that the temperature here has to be in Kelvin. It's given in Kelvin, so that's good. And we can proceed with plugging in those temperatures for our T1 and T2. The volume, it doesn't have to be any certain unit as long as the units match. And here the units match, they're both liters. Pressure that we'll find will be in atmosphere because the pressure we're given is in atmospheres. Okay. The temperature, though, can't be Celsius or Fahrenheit, has to be Kelvin. So let's plug these in. Here I'll say initial is my P1, 1 atmosphere, times V1, 10 liters, over T1, 300 Kelvin, equals P2, that's what I'm trying to solve for, times V2, 20 liters, over T2, 600 Kelvin. And so here I've set up the equation of the combined gas law. I've plugged everything in, and now I have to solve for this one unknown variable, P2. Right? I do that with algebra. Multiply both sides by 600, so this drops out here. Divide both sides by 20 liters, so this drops out here. And now I take 600 times 1 times 10 divided by 20 divided by 300 to calculate P2. And in this case, the way it works out is P2 is also going to come to 1.00 atmospheres. Okay, so I can still use the combined gas law in this setting where pressure actually isn't changing, but I didn't know that going in. In retrospect, if the volume is doubling and the temperature is doubling, those two things offset, so nothing has to happen for the pressure. It doesn't have to compensate for that change. Right? As the volume doubled, the temperature doubled. So the pressure was able to remain constant. But we used the combined gas law here to figure that out. So this is an example practice problem of combined gas law. Again, you'll be given 5 of the 6 possible parameters, and you have to solve for that 6th one. Now, this brings us to ideal gases and the ideal gas law that we will get into on the following slide. So gases are pretty chaotic systems, okay? They're these microscopic atoms and molecules that are have a low density, so they're spread out, but they're moving around quite fast and chaotically, right? Whereas a solid is just more or less sitting there with the molecules arranged in some lattice, okay? But gases are much more chaotic, and so we make approximations so that we can calculate properties of these gases. And the approximations we're going to make are sort of lumped in to consider this an ideal scenario, this ideal gas. We're going to pretend it behaves predictably and consistently. And so that we'll have these following properties. Gases are made of molecules with tiny volumes. That seems like a good, approximation, that these volumes are really, really tiny. Makes sense. Molecules are really, really tiny. they're existing in some large room, right? So the molecule basically takes up no space. Its volume is so tiny compared to the large dimensions of the room around us. Okay, so the gases have very tiny volumes. We're going to assume they move in rapid straight lines and travel randomly, right? So this molecule moves off in this certain direction in this straight line. It's not like it's curving about and traveling in some weird zigzag pattern, right? The math gets much more complicated considering that scenario. We're going to assume they're just traveling in straight lines, kind of like, billiard balls on a billiard table. They might collide with one another, right? But they're basically traveling in these straight, predictable lines, not randomly. That seems like a fair assumption. We're going to assume they're not attracted to each other, right? So if they do collide, they collide without losing energy. They're not making new compounds, right? So when this molecule is moving in this straight line direction and meets up with another molecule moving in this straight line direction, they go whizzing off after the collision in these certain predictable directions, right? As they bang into each other or collide into one another. Okay, and we're assuming they're not losing any energy. It's not like they're, rearranging their electrons as a result or getting excited in any other way. They're just colliding and continue to move in these different straight lines. We're also going to assume the average kinetic energy is proportional to the temperature. Okay, so the temperature here really is a reflection of the kinetic energy of these gases. And so this is basic kinetic theory of gases applied in this ideal gas case. So with these assumptions, you can do a bunch of math and calculate the ideal gas law. And the ideal gas law is very powerful because it connects pressure, volume, and temperature with the moles of that gas. Okay? You'll notice before when we use Boyle's, Lusak's, or this combined gas law, or Charles, right, it was about some change of state, right, where we were taking the pressure and changing the pressure, or taking the temperature and changing the temperature. This ideal gas law statically can tell us what is the pressure in this room if I know the volume, the number of moles of gas, and the temperature. Or in this room, if I know the pressure, maybe I measure that with a barometer, the volume, maybe I measure that with a ruler, and temperature, maybe I measure that with a thermometer, well then I can calculate the number of moles of gas in this room. Okay, so this is a very static formula, but very powerful. R here is a gas constant, and it has the value of 0.0821 liters times atmospheres divided by moles times Kelvin. So basically this R here is a constant, never going to change, but it takes care of the variables. Right? You'll notice on the left side of the equation we have pressure times volume. Right? Pressure is like atmospheres, volume is a unit like liters. On the right side we have temperature has to be Kelvin, N, which is the moles of the molecule or atom. So R is taking care of converting this unit, liters times atmospheres, to something that's like moles and Kelvin. And so those are the units in this constant. This constant is really just taking care of units, making sure the units all work out. Okay, so that we'll see when we multiply atmospheres times liters on the left, we get R, which has units of atmospheres times liters over moles times Kelvin, and we're multiplying it by N, which has moles, and temperature, which is Kelvin. So the units on the right will also work out to be liters times atmospheres. Okay, so what's important here is that this number of R, there are different versions of it, but this is the one I use for my class. This version of R has these specific units. Okay, so pressure has to be in units of atmosphere here. Volume has to be in units of liters. This is different than, say, Charles' law or the combined gas law. Similar to those laws, though, temperature does have to be in Kelvin here, just like it always is. Okay, so there are some restrictions here. So, be on the lookout if your pressure is not given in atmospheres, convert it to atmospheres first. If your volume is given in milliliters, well, multiply it by 1,000 to get to liters first, before plugging it into this formula. So let's take a look at a typical problem for an ideal gas law. So if 1.06 moles of helium exerts a pressure of 0.750 atmospheres at 210 Celsius, what is the volume in liters? Feel free to pause the video here and try this yourself, remembering PV equals nRT, before watching me solve the problem. Okay, with these gas problems, I typically read it over once, as I've done, and now I read it over again and identify each of the parameters. 1.06 moles, that's N, of helium exerts a pressure of, this is P, 0.750 atmospheres, at 210 Celsius, that's temperature. What is the volume in liters? P. Okay, let's write this down. 1.06 moles is my N, 0.750 atmospheres is my pressure, 210.0 degrees Celsius is my temperature. What is my volume? Okay, so clearly I'm going to have to use this equation here, P times V equals nRT. R is a constant, usually given to you or you can look up, and it has the units liters, atmospheres, moles, and Kelvin. So the first thing I'm going to do is make sure all of these numbers I'm given are in these units. Pressure is in atmospheres, so that looks good. Volume is asked for in liters, so that looks good. Moles is provided in moles, so that's good. Temperature is not provided in Kelvin, it's provided in Celsius. So I have to take this 273 and add it to 210 to convert from Celsius to Kelvin. There. Now my pressure, my temperature, my moles are in the correct units, and I can plug them all into PV equals nRT. So let's do that. P is 0.750 atmospheres times V, well, that's what I'm looking for, that's my unknown, equals 1.06 moles times R times 483 Kelvin, right? Where R here is this 0.0821 liters atmospheres per mole Kelvin. Okay, so now to simplify this to solve for V, I'm going to divide both sides by 0.750 atmospheres, divided by 0.750 atmospheres. And now let me write out my expression for this V that I have solved. It is 1.06 moles times R, 0.0821 liters times atmospheres over moles times Kelvin times 483 Kelvin divided by 0.750 atmospheres. Now I can make sure all my units work out. Here's a mole divided by a mole. Here's a Kelvin divided by a Kelvin. Here's an atmosphere divided by an atmosphere. I should be left with liters, which is good because it's a volume I'm after. So now I take all these numbers, 1.06 times 0.0821 times 483 divided by 0.75, and I get an answer at the end here of 56.0 liters. And that should be my answer here at the end. Okay, so that's an example of an ideal gas law practice problem. Notice here that temperature wasn't in Kelvin, so I converted it. Also pay attention, maybe the pressure is in torr or millimeters of mercury, and you might have to convert that to atmospheres, right? Or your volume might be given in milliliters, but you need it in liters. So just pay attention to the units, make sure to write them all out as you solve these problems. That'll do it for this lecture on ideal gases, the ideal gas law, and combined gas law. As always, feel free to like this video or subscribe to YouTube, or catch me over on Twitch every week where I hold my office hours for my classes, but are open to everybody. Feel free to drop by there and ask whatever chemistry questions you might have. That'll do it for today's lecture. See you next time.